Okay, so I don't know, last time we were together, one of your classmates, they sent out through the messaging system this code for you guys to decode, or maybe it was sent to me, I don't know, but thought it might be fun for you guys to look at it, see if you can figure out what this says. I don't know if you got a chance to jot it down, but if not, I'll send it out to everybody. So maybe we'll talk about it on Monday. So see if you can figure out what this says. I'm not going to say who the student was because then you'll just ask them. And you want to make sure that you take a look at this document. We'll talk about this on Monday, but we need to start thinking about an exam. Won't be next week, but we need to start thinking about it. So our first exam, we're going to cover these points, and there's only 10 points, but actually in this first one here, there's a lot. That week one objective sheet, there's a lot of material there. So this will cover weeks 1 through 5, I believe. But again, I'll say more about this on Monday. I just want to make you aware that it is out there. So if you go to your Canvas, you'll see this document, and you can start thinking about scheduling some time to start and go back and kind of look at this stuff. And then if you have any questions, of course, we can talk about it. But today, what I want to do is to go back to a conversation we had the first week of school. We talked about logic, and we're going to learn about a new device called a logic gate, and show you how you can use these gates to translate a problem. Maybe you have a problem a descriptive problem written in the English language, and you like to implement it in logic. You can use it for PLC or just general programming. You can actually use gates to help you do that. So we're going to look at gates, and there's actually a system of algebra that goes along with these gates called Boolean Algebra. We'll talk a little bit about that, and then we'll see what else we can fit in for this morning. Hopefully you guys are staying safe out there. I'm kind of stuck down here. I'm at my mom's place now. She lives over by Cincinnati Zoo, and you have to go up a steep hill and down a steep hill. So I'm kind of been snowed in since I guess since Thursday night. Actually Wednesday night, I think. I don't think I went anywhere yesterday. So, but anyway, we want to look at logic, and we want to learn how to duplicate logic on the PLC. We talked about this idea, this concept called the binary concept. I don't know if I used that term before, but the binary concept means that you can have a device or you can have a machine that can be in one state or another. It can be on or off. It can be a motor could be running or not running. Anything that can be considered to be in one state or another is a really good candidate for a PLC. And so this idea of a binary concept is also a good candidate for logic, since being in one state or another can be represented by binary digits 0 and 1. And so we looked at basic logic functions. We looked at the 3 basic logic functions. If you remember, we looked at the AND function, we looked at the OR function, and we looked at the NOT. Those are the 3 fundamental logic functions, and there are actually others, but the other ones are kind of built from the basic ones. So we'll show you a couple of other ones today, some new functions, and talk about the logic behind the functions. But just understand that the new ones are kind of derivatives of just kind of putting these basic ones together. What you're looking at now is kind of a representation of a gate. Now each gate, there'll be a gate. I'm using the term gate. A gate is a physical device. It's not software. It's something you can actually go buy at the electronics store. You can buy an OR gate, and you can buy an AND gate. So these are not the symbols for gates, but this is just kind of a general way of showing the gate. But the point is that you have these logical functions. Now, when we talked about the AND function, for example, we showed you 2 switches in series, at least 2. It could be 2 or more. All the logical functions require at least two switches, or two, for switch we'll use the term input, two inputs or more, and that's true for all gates or functions except for one that we call the not function, or we'll use the term inverter. So you'll see these boxes on this slide, and what's inside of the box is like a circuitry to mimic, trying to get my drawing thing here. So inside of this box here is circuitry to mimic the switches that we talked about. So what I mean is, you remember that the AND function, you can represent the simplest AND function or AND circuit with two switches, two single pole switches in series. Well, there's actually solid state devices inside of these things that we call integrated circuits, or IC chips, that make up the device. And they're not really switches, but they're these switches called transistors. And we kind of mentioned transistors when we classified PLC outputs. If you remember, there was a transistor, triac, and relay. Well, a transistor is just a special kind of a switch, solid state switch. Thing is, we can make these devices really tiny and put literally millions, and in some cases billions, of these little switches on a really small area. So kind of the world is kind of built on these silicon chips. So without getting too detailed, you can actually use these transistors to implement those switches in series for the AND, or the switches in series for the OR really any logical function. So we really don't wire switches in series. I mean, they used to. You guys, when you did your PLC history assignment, the first homework, they used to use not so much switches, but relay contacts in series or parallel to implement logic. But now we can do it in solid state. And remember, solid state means no moving parts. We can actually do it with these little special transistors called, these little special switches called transistors. And so each gate, we'll talk about several gates, but each gate is going to have a symbol associated with it. And you need to know the symbol. Each gate will have a rule associated with it. And each gate will have a mathematical expression associated with it. Now, the mathematical expression, the algebra of logic or logic circuits, is called Boolean algebra. So we'll call it the Boolean expression. So when you hear the term Boolean, it's just the algebra that applies to binary systems. So we'll talk a little bit about that today. But so logic, what is logic? We gave you a definition at the first week. People are signing in, and my thing is beeping here. So we gave you a definition of logic the first week. And you know that logic is the ability of a circuit to make decisions based on certain predefined inputs. And these predefined inputs, we kind of showed you the predefined inputs. That was a table that we talked about the first week of class, but we'll show you more of that today. But logic is the basis. It says here the basis for the PLC, but really logic is the basis for any digital device. Your computer, every digital device uses logic to function. PLC specifically, we program in logic. We programming in logic, ladder logic and other types of logic, but we actually programming is logic, and that makes it a little bit different than a normal PC. I don't think this slide is too important. Basically, there's two types of logic. There's what we call positive logic and negative logic. And I mean, I've honestly only seen and used positive logic, but basically the difference is in positive logic, the active state, when we say active, you can use the term on, you can use the term true, you can think of a voltage level, or you can think of a 1. So the active state would be a 1, and the inactive state would be a 0, or the true state would be a 1, and the false state would be a 0. And then negative logic just reverses that. And like I said, I've been into this stuff for a long time, and I've actually never, ever seen this in use. So I probably could take that slide out. But let's go ahead and review the basic logic functions. We talked about this the first week of class, and I showed you how you would implement these functions using switches. And so we'll review the same kind of thing today. We'll look at switches, the circuits, and I think it helps to understand how you would actually wire this up physically using switches or relay contacts, but just realize that there are actually these devices that use those special switches called transistors. So you never really have to wire anything up. It's just a device that will implement the switches in series, or will implement the switches in parallel. And we'll look at that. The first one to talk about would be the AND function. So let me say a couple things about just kind of the way this is drawn. First of all, this thing right here is a gate. So it has a particular shape. It has a particular shape, and let me erase this. The other thing to notice is that the inputs are drawn over here. Typically, when you draw these gates, you draw the inputs on the left and the outputs on the right. So this shape right here is unique to the AND gate. In a second, we'll talk about the OR gate. It'll have a different shape. But you always draw the inputs on the left and the outputs on the right. Now, having said that, when I was going over these PowerPoints, for some reason I have the gates that come after this, the OR and a couple other ones, I have them reversed. I'll point that out to you. But notice the shape of the gate. This is the shape. This, when you see this, you want to recognize that as an AND gate. And remember what I said earlier, all gates have at least two inputs. I mean, I show two here. You can have three. You can have as many as you want. You just can't have one. The only gate that has a single input, well, we'll talk about that one, but that's called the inverter. The other thing to notice is that we represent the inputs with letters of the alphabet, and typically we use letters from the beginning of the alphabet to represent inputs, and we use letters from the end of the alphabet to represent outputs. And what is this right here? Well, remember we said that logic is the ability to make of a circuit to make decisions based on certain rules. Well, the rule is actually called a truth table. And so each gate will have a couple things you have to know. Each gate will have a symbol like this one. Oh, wait a minute, I know how to stop that. Okay. Each gate will have a symbol. Each gate will have a truth table. And each gate will have a mathematical expression called the Boolean expression. And looking at any of the three, you should be able to recognize the gate. So if I show you the gate symbol, you should be able to recognize it as, let's say, as an AND gate. If I just show you the truth table, you should be able to recognize it as the truth table for AND. Or if I show you the Boolean expression, which we'll come to here in a few minutes, you should be able to recognize that and say, hey, that's the expression for an AND gate. Then you have the AND gate application. Now this is where we kind of relate it to an actual physical hardwire switches or contacts. And we've done this already. This isn't anything new. You've seen this, but basically the fact that AND logic is implemented with switches in series or inputs in series means that if the thing I want to happen is for this light bulb to come on, and we say that if the light is on, we use that as a true condition. If it's off, it's a false condition. Or now that we know binary, we can say we're going to assign the onness of a light, if I can use that term. That'll be represented by a 1 in the PLC, and the offness of a light represented by a 0. The only way to get a 1 on the output is for both of these switches, to switch A and switch B, to close, because you got to have a current path to the load, to the light bulb. And so the AND circuit makes sense that switch A and switch B have to be true being closed, in order for the output to take place, in order for the output to be true. Guys, I have a dog in a cage, so I apologize. You might hear him. Oh, wait a minute. Hold on a second. Yeah, so my mom has she has a chair, a living room chair, and part of it was sticking inside the cage, and I heard the dog was trying to eat the chair, so through the cage. But anyway, that happens when you're doing stuff from home. Okay, so here's an example. So instead of drawing this and thinking about it this way, I think in the back of your mind, you want to just kind of understand that the AND operates like this, but all we're going to deal with is this. So when you see this, I want you to think about this circuit and think about this truth table. Now, eventually what we want to do is you want to represent, we don't even want to have to deal with a circuit. We want to abstract from all of this and just deal with an equation, because we can do things with the equation that sometimes that abstracting from a physical circuit, you can see things in the equation that you can't really see by looking at the circuit. I should say not see, but do things that we can do using the math, the Boolean expression that you can't see easily or do easily looking at the circuit. So the and we looked at, so that should be familiar to you. And then the or. Now, actually, I think the or, I don't know, I made these slides a long time ago, but I think the gate symbol actually has a little bit more of a point to it like that. So number one, there should be more of a point to this. And then the other thing is I have this flipped the wrong way. So remember I said that we show the inputs on the left and the outputs on the right. So I should have this turned the other way. I don't know why this is flipped. I don't really, I'll have to fix that. But the point is that here's a gate symbol for the or, and then you have the rule or the truth table for the or. And then in a second, we will talk about the Boolean expression for the or. And you already know from a previous discussion how you would think about switches in an or fashion or or connection. Those would be switches in parallel, because for or, what you need is any or both conditions to be true in order for the output to be true. That is, either or both switches to be closed in order to get a true output. And so the or can be represented by contacts or switches in parallel. And then again, the rule or the truth table is as shown. And then finally, we talked about the not function. Now, for the not function, we'll use the term inverter. So inverter and not mean pretty much the same thing. They use the term invert because what the inverter does, since we're going to deal with binary, deals with bits, it will take a bit and it'll flip it. So remember when you took the 2's complement, how you flip the bits? Well, one way you could do that is using this device called an inverter. If you put in say you put in on the input, you put in a 1, then it'll change that to a 0. Or if you put in a 0, it'll invert that and change it to a 1. So that's kind of what this does, and that's what the truth table is showing you. Now, what about this not A? You see how this has a bar on it over the top of it, that variable A? So if you want to show something that's been inverted or knotted, you draw a line over it like that. And there's actually another way to do it. Sometimes, and I'm drawing with my mouse, so I'm not the best with this, they'll put like a little prime symbol right there. So you call this A not or not A, or A prime A. This is just a variable that's been inverted. So if I set the value, well, here in the truth table, it shows you that if you set the value of A is a 0, then when it goes to the inverter, and that it being the signal, it's going to change it to the opposite state. And that's kind of what the inverter does. So I want to zoom in a little bit on this little bubble thing, because that actually is pretty important. So I think the next slide deals with that. Okay, so that little bubble is called a state indicator. Now, you can look at this any way you want, but here's how I think about it. I actually think of 1s and 0s moving through these devices. 1s and 0s moving through. So what happens is, let's say you got a 1 on the input. That's that digital pulse, that positive going digital pulse. And it's a pulse if we're going to move it. And so when that 1 moves into this gate, it's still a 1. But I want you to think of when it hits this bubble, the job of this bubble is to change it to the opposite bit. So when that 1 hits this bubble, then it becomes a 0. So over here, you got a 0. Or when this is a 0 over here, when it hits that bubble, it changes to the opposite bit. Now, I'll point out in a second why I want you to think of these bits as actually flowing into the chip, into the device, and not doing anything, not changing state until they hit that bubble. I'll come back to that. And then the circuit representation of not is just to use a normally closed push button. So, and the thinking behind this is a little harder to see, but the thinking behind it is truth table. So not pressed, we call that a 0. Pressed, we call it a 1. If the button is not pressed, the light's on. True state or a 1. If it's pressed, then the switch would open since it's normally closed, and then the light true state would be off. So we use this to represent the inverter physically. Then you get to the point to where you can actually take these gates and you can start to combine them. So remember earlier I said that there's 3 fundamental gates. It's kind of like chemistry where you can take basic elements and you can combine them and you can get compounds and mixtures and all of that. Well, the gates are the same way. You have over 100 elements in the periodic table, but we only have 3 basic things to deal with in logic. We got and, or, and not. But you can actually take the and, or, and not and put them together, and you can make more, you can make what we'll call derived logical functions. So a NAND gate, basically a NAND gate is I would take, and I'll try to do my best to draw this. Let me see if I can zoom in on this. What you do is you take an AND gate, and you take an inverter, and the inverter has the little circle thing on it, and you run the output of the AND gate to the inverter, and then you take on the output of the inverter would be the output of the total circuit. And so basically this, in this equation, this is the not part and this is the and part. Well, rather than draw it this way, even though we know a NAND gate is 2 gates together, a not and an and, what we do is we just draw this symbol right here. We just draw an AND gate, and notice that bubble right there. Remember earlier I said that state indicator, I want you to think of the bit changing state when it hits that bubble. Well, now you can see why, because we're going to use, instead of drawing the whole inverter, if I want to show a bit that's been inverted, we don't have to draw the whole inverter like this. What we do is we borrow the state indicator from the inverter and we just attach it to the AND gate, and then we rename it. We call it a NAND gate. Let me see. Somebody just sent me a message. Guys, I'm sorry. I'm using a laptop and everything. Okay. Jacob says, would an example use of this be like an e-stop? Not you. I'm not sure you use this particular function, Jacob, for e-stop. Actually, it's funny that you say that, because your first lab you're going to deal with, well, we won't call it the e-stop, but one of the things you'll do on your first lab assignment is you'll deal with a 3-wire circuit. They call it in industry a 3-wire circuit. It's a stop-go circuit, or start. I don't know why I can't talk this, but start-stop circuit, and you'll deal with that. But I don't think they would use this for that particular application. And we'll show you that, and not so much with gates, but we'll show you that using the symbols that we use to use logic in the PLC. We don't actually use these gates in the PLC. There's actually instructions that represent inputs, and then depending on how you put those instructions together, you actually build these logical functions. What these gates help us to do is to, let's say a person gave you, you're going to program a PLC, or I'm saying PLC, but any kind of logical, basically any language, any computer language, and the language you use, one language you use to program a PLC is called ladder logic, but there's others. So this, what I'm going to say applies to not just PLCs, but anything. Given the problem in say I give you a problem and I state the problem in English, I write it down. I don't know anything about programming, but I do know what I want to happen in my factory or my device. I can just kind of write it down in English. You can look at it, and there's going to be and, ors, nots in there. You can actually take the English and you can represent the logic of the say the paragraph or the English statement with these gates, and then you can take these gates and you can translate these gates to a Boolean expression or directly to a PLC program. So these gates are not so much to, I mean, you could implement a e-stop using gates and kind of think about the logic of it, But these gates are really meant to help you understand how you would go, or one application is to help you to understand or to see how you would go from an English down to something that a PLC can use, a program. So we'll actually show you some of that when we get into more into the course. But that is a good question.
Okay, cool. Thank you.
Okay, let me get back to my. I don't like. You guys. I don't know if I mentioned this or not, but I don't have a cell phone. I don't have a flat screen. I don't have a TV. I don't have any of that stuff. So I'm not. I hate this two. You guys live in this two-dimensional world where you're working on your screens on the cell phone, and then the screen here is so tiny. I feel like I'm looking at a. So and everything's just kind of folded in on itself. So I like a big screen when I am working on the screen. So let me get back to a PowerPoint. Okay, so this NAND, I think now. So look at the output. Now I don't know if you remember. If you remember the output of the AND for the AND gate in this output column here, the only time an AND was true was when both switches were closed. That was right here. So it was a 1, and all these other inputs were 0. The output column for the AND was a 0, 0, 0, 1. So that's what you have up to this point right here. But once that hits the state indicator, then all those bits are inverted. So you'll look at this table, and if you compare this to the output truth table for the AND, you'll see this is the exact opposite. So basically, the NAND gate takes the AND gate and inverts it. And the way that the language we'll use, we'll say it knots it. It knots it. And you can do the same thing with the OR gate. We can take a basic OR gate and we can connect. And again, I don't know why all my ORs and NORs are drawn the wrong way. That's really weird. Must have been something with the program I was using, because the ANDs, they seem like they're okay, but these are all reversed. But anyway, we've done basically the same thing here. We took an inverter, we add to an OR gate, and you guessed it, we get a NOR gate, a not OR gate. And so if you remember the output of the OR, this is going to be an interesting video. If you remember the output of the OR gate, the only time you had a 0 is when both switches were open. That's the parallel circuit. So you only had a 0 here. For all other states, you had a 1. Well, this is exactly the opposite. A NOR gate is the opposite of an OR gate. Now, remember, okay, I mentioned Jacob asked about using the previous gate, the NAND as an e-stop, and I mentioned the fact that what we're going to do, really going to take, we need the ability to go from English to a program, to a PLC program, from words to ones and zeros. Well, it turns out there's a problem with the word or. And means just one thing, and I mean in logic. In logic, and this and that means that both conditions have to be true. But or is a little confusing. Or can mean, in English, can mean two things. When you say one or the other, sometimes when you use the term or, you mean one or the other, but not both. And sometimes you mean one or the other or both. So let me think if I can think of an example. I don't know. If somebody said you want ice cream or cake, and you say, well, I want both, so they give you both ice cream and cake. But you might, let's say you take your girlfriend or boyfriend or whoever, you take your significant other out to a restaurant, and you sit at the table, they give you a menu, and you read the menu, and you read, and it says you can have, with the entree, you get your entree, and you can have a soup or salad. That sense of or, they don't mean you can have both a soup and a salad. That means you can pick one or the other. So in English, sometimes or, I'm talking from a logical point of view, sometimes or means one or the other or both. Sometimes or means one or the other, but not both. The example I gave you was one or the other, but not both. So sometimes if I go back to, let me go back to the OR. So here's the OR. Sometimes what you want to do is you want to exclude the condition right here. You want to exclude this condition because you mean the dinner example I gave you, you mean this, one or the other, but not both. You don't mean this one. So I have to be able to pick up that representation of OR in a computer or in logic. And the way you do that is by using something called the exclusive OR. And so if you look at the symbol, notice it's just again, I have this drawn the wrong way. There's just an OR gate, and they put this mark right here. So this is what differentiates an OR from an exclusive OR. But more importantly, if you look at the truth table, look at the condition they exclude. Exclusive OR, because we exclude the condition where both inputs are true. So if you're actually going from English prose, from words to ones and zeros, or from ones to logic or some kind of program, you got to be able, from the context of the problem, you have to be able to read it and know which meaning of OR is meant, and then you can implement that using either this symbol or the OR symbol. So this is the exclusive OR, and this is called the XOR. Actually, this one, you probably want to put a little note if you have printouts. I mean, you probably don't, because I didn't realize I didn't unlock this. I didn't unlock it until yesterday. But this exclusive OR, this turns out to be pretty important in PLCs. What is an interlock? Anybody? Well, I know I have one PLC expert out there, but what is an interlock? You might have an interlock in a if you work in industry, they talk about interlocks. What is an interlock, or what does it do? Anybody?
Well, I guess it depends on what kind of interlock you're talking about.
Okay.
On the most basic form of an interlock, I think of a signal or hardwired device in between two separate systems, in which one is feeding an output from its system into the other system, saying, hey, this e-stop is okay. Hey, we're running. Oh, the pressure over here is okay. And depending on the requirements for the system, the other system can also feed back a received signal okay. It also doesn't necessarily need to be hardwired. You can send that same thing, a same kind of interlock over Ethernet, Circos, whatever communication network you're using. The only difference is if you're using a communication network, you typically need to send up some kind of heartbeat message between them, so that you know that if the state's not changing, you haven't lost communication.
Okay, so now you guys know who one of our PLC experts are out there. So here, what we want to do with interlocking, thank you, Mike, is and he mentioned it depends. We said it depends on the type of interlock we're talking about. So guys, you're going to learn just enough in this class to be dangerous. This is not, you're not going to go out and you be an expert PLC programmer. So this is just enough this is a kind of an entry level basic class. And so what we mean here is that when we want to make sure we have two or more events, we want to make sure something's not happening. We can do that with what we're going to call software interlock. And you can actually use this kind of logic to, if you look at the truth table, you can use this kind of logic to make sure if I want to have two or more events happen, we'll just focus on two events. We want to make sure they don't happen at the same time. You can use what we're going to call software interlock. And we'll revisit this, but I won't remind you of this circuit, but I'll ask you when you look at the Boolean expression of this, if this looks familiar, and I'll be referring to this XOR gate. We can actually use this to prevent things from happening. So that's the sense we mean the sense of the word interlock when we use it here. We're gonna get into this, and I'll be honest, guys. This is more for how. Well, I'll put it like this: there's a list of these rules. If you guys were electricals, you would be required to remember these rules, and I'll display them in just a second. You'd be required to remember these rules, And to these rules apply to this system of mathematics that apply to binary systems we call Boolean algebra. And you would be required to know and to use these rules. And normally, when you're studying this stuff, you go in and you learn the rules, and then you apply it to a bunch of logical circuits to get good at using the rules. And just when you get good at it, then we introduce another way to use these rules kind of more mechanically, which you really don't even have to know the rules. You can actually, there's a way to get around what the rules are for. And let me just say what the rules are for. These rules, these Boolean rules, are designed so that you can take a logical function and you can simplify it. You can reduce it. So these are, think of them as reduction rules. So we'll have you go through these rules. Now I'll show them at the end of this PowerPoint. But here are a couple right here. Here are a couple, not a couple rules, but here are some, here's some examples of what we mean by Boolean algebra. And so what those rules do is it takes Boolean algebra, a little bit more complicated expressions, and it shows you, not methods, but it gives you ways of reducing them. And it's a little hard for me to describe, but you'll kind of see it in action. So I'll show you this list, but it can be a little overwhelming when you look at these rules. But we're actually going to learn to do our reduction another way. So what I mean by reduction is we want to take a complex logical circuit and we want to reduce it down to the simplest or the fewest number of gates and not use any of the lose any of the functionality of it. And you can use that using Boolean algebra. So what is Boolean algebra? Well, I mentioned that every function, every logic function is going to have a gate symbol. We talked about a couple of them. It's going to have a truth table. And we talked about those. But it's also going to have this expression we call the Boolean expression. And so in a second, when I show you the rules, you'll see these letters, but you'll recognize that when things are, if you look at this, this kind of looks like A and B are being multiplied together. There's really an operator between those. And I'll see if I can draw this with my mouse. There's a little dot. I'm trying to draw a little dot. And that dot is the operator. This right here is the operator for that. So if I'm, say I had an A and a B on the input of these gates, and I want to show basically using symbols or Boolean algebra, I want to show the AND function. What I would do is I have an A and a B, and I put this dot in between them. This is the operator for AND, whereas this down here, which you would call a plus sign, that's the operator for OR. This is not A plus B. That's not the way you think about it. You think about it more like this. We're just using that plus operator to represent the OR function. So I'm showing this dot because just like in regular arithmetic or math, when you multiply, you can put the cross in between or the dot in between them, or you can just take them off, and then one variable right next to each other, that means a product, A times B. We can think of it the same way when you're ANDing. Strictly speaking, when you're ANDing, we're going to use this symbol right here, the dot, but you can just write it like you would write a product of variables, and it's understood to mean ANDing. And we'll do that throughout the course where we won't write the dot operator. I mean, you could, it just takes an extra step. But anytime you see a multiplication in logic, a Boolean algebra, then what you're doing is ANDing. If you keep that in mind, then you won't have any trouble thinking about the Boolean stuff when we get to it. So you want to know that the dot is the operator for AND, the cross is for OR, and then this little thing right here, that's for NOT. So if I take A and then I have another A, but I put a bar on it, then whatever value, these variables can only take on one state or another. It's going to be a 1 or a 0. So whatever value A has, then A NOT's going to have the opposite value. So that flips the bit, and we'll represent that. Now sometimes as I mentioned, and this is a handy kind of notation, instead of having that bar, they'll have a prime. You'll see here, I don't know if I have it in this PowerPoint, but sometimes you have to take a whole bunch of variables together inside a set of parentheses, And if you want to knot that whole thing, you put a bar across the whole thing like that. Well, that's fine if I'm drawing it on the screen like this, but in Microsoft Word, I don't know how to make that bar across the whole thing. So then I can just take it and just put a little prime right there. And that means that whole thing is knotted. So I can use that instead of this. So you'll see both of these used. So that little prime symbol, it means not, that you're knotting the variable or inverting it. And then you have the ones for the derive gates. And so this will make sense. I mean, if I have the product of two variables, if that means and, then if I put a bar over the top of it, then that is the NAND, the not and, or a not or. So the NAND, you want to be able to just look at that and say, hey, that's a NAND, or hey, that's a NOR. Now this one, the XOR, is kind of similar to that, but the show is not a regular OR, XOR. That circle should be centered. I just couldn't get it centered, I guess, when I made these slides. So if I took it, if I take that OR sign and I put a circle around it, then that indicates a XOR. Okay, so this is just kind of, when you use these, you get used to them. It's not that bad. Now we talked about those rules. So these are not, this is not all of them. The rules and law, these are the laws, but there's laws and there's rules. And I'll display those here in just a second. But some of these make sense actually from your regular algebra, like the commutative law. You know, addition is commutative, which means the order that you add things or the order that you multiply doesn't change the outcome. Well, ORing is the same way. ORing and ANDing, it doesn't matter, you know, what inputs I OR first or which inputs I AND first. It doesn't matter. So there's a commutative law for ANDing and ORing in Boolean algebra. And then the same with the associative law. There's one for addition when you're adding and when you're multiplying. Well, the order in which I over here that I OR these, it doesn't matter if I OR A and B together and then OR the result of that with C, or if I do it the other way, the outcome is going to be the same. So these first two make sense. And even down here, there's a distributive law, but the one you really got to think about is this one. And I'm not going to attempt to explain it, but one of the things we'll do in here is to prove things are logically valid. You can put them in what we call the truth table. You can actually build a truth table to check the validity of a function, a logic function or statement. And you can actually do that. You can put both the left and right side of these in a truth table, and you'll see when you evaluate the truth table that they come out to be, we say, logically equivalent, which means that both the left side and right side is doing the same thing. If you have to implement this in a program, you know, you have three inputs, and over here you have four inputs, even though one of these is repeated. If you were to draw, and we'll show you this on Monday. I'm not going to do it now because I can't draw these gate symbols on my screen. But it's much easier to draw this one or to implement this one than it is the one on the right. So this is the way to go from a complex group of inputs to a less complex group of inputs. It's a way to think about it for right now. We use this system of Boolean algebra to reduce logical circuits, which ultimately has the effect of making the program a little bit less complicated. The most important thing, and I don't have this law with the listed with the other ones, but this is really, really important. This is called De Morgan's laws. I'll be quiet and give you a second just to read this, and I'm not going to read it. I'm going to explain it in the next slide. So you take a second and read this. And then I want to show you in Gates. When you read it is one thing. When you see it in Gates, using the Gates, it makes a little bit more sense. And again, you can put any of this in the truth table. Now, maybe Monday I'll demonstrate this. You can take any of this and put any of these rules or laws in the truth table, and you'll see that they're valid. But basically, what this does is it takes a gate. Now this is our Nand gate. It takes our Nand gate and it changes it to one of our OR gate. Now this OR gate is interesting because if you think about it, when I showed you the OR, it looked like that, right? And then if you put a bubble on it, then it changed it to a NOR. So that would be like taking A and another variable B, and you will OR those together. That ORs them together. But then when you add that bubble to it, you're knotting this. Whereas what I have right here is that's not that. Well, here you're taking, well, actually I have it on the slide already. You can see it. Here what we're doing is we're taking, if you think of a bit like a 1 going into this bubble, it hits that bubble. If it's a 1, then it's going to be inverted. And then this is going to be inverted separately. Whereas if I had a regular NOR, I get the 2 bits going into the chip, into the gate, and they're not inverted until they come out the other side. So you take the whole expression and invert it, as I had before. You put that line over the whole expression. Notice here you have a line over the A and a line over the B. And that line is broken. And so this is not, it's not an OR gate because you got the inverter, you got the state indicators there. It's not a NOR gate because the NOR gate would have the bubble here. So what is it? What do we call this? Well, anytime you have the state indicators on the inputs of a chip, you call it the negative gate. So this would be a negative OR. If this was an AND gate, this would be a negative AND. Okay, so we'll come back to that. But the point of this, De Morgan law, is we take a NAND and we can implement its logic with this negative OR. And you'll see it works with a NOR also. But what I want you to really look at is this right here. Because you got to be able to do this. You can see it right here using the gates. I mean, we kind of walked you through it that if you walk through the logic of going from here to this, you looked at that, let's say in the truth table, you'll see that the outcomes are the same. You'll see that this statement is true. But what I want you to take away, that I want you to see, is that not so much how you do this with gates, but how do you do this with, how do you go from this to this? How do you do that? Well, the trick is that if I use the term demorganize, I give you a expression and I say demorganize it, that means something's knotted because this only works with either the NOR or the NAND. So you're going to have this bar, that not symbol. And what you do to demorganize it in algebra, you just take this line and you break it, and then you change the sign. Now this sign here is a dot. So if you remember this, break the line, change the sign. Break the line, change the sign. That's what I mean by De Morgan. So then you don't have to understand any of that down here. If you look at this and say, all right, I want to demorganize it, I'm going to break the lines. That means each individual variable gets, the line is broken. And then whatever the sign is here, if it's a dot, I'll change it to a plus. If it's a plus, I'll change it to a dot. And then this will be demorganized. Now, when I get to a whiteboard, we can show you, a little bit better that these two are actually logically equivalent to each other. And as a matter of fact, I think in one of your homeworks, you have to actually prove one of De Morgan's laws, and there's actually 2 of them. So this is the first of the 2. The other one is just the opposites, where you start with the NOR gate. So as I said, you have all of these, the whole output is knotted. If you apply what I said a second ago, all you really got to do is break the line and change the sign. So the line is broken, and then I put a dot in there instead of a plus. But both the left and the right side of this are logically equivalent. Now, there's a reason why you want to do this that relates directly to PLC programming using ladder logic. And, when we get, I guess next week, we'll talk about your simulator and we'll talk a little bit about the instructions that you'll use. But we'll come back to this and you'll look and you'll see why, if given this, there's no way to implement this in the PLC using PLC logic. But with this, you can do it easily. So sometimes the English statement that you're dealing with, sometimes it'll give you this and you'll say to yourself, well, hey, there's no way for me to implement that in PLC logic. So then if you know how to demorganize, you can change it from this to this, which you can implement. So I know that probably isn't real clear, but I promise you it'll be more clear when we actually get to using the ladder logic in the programming. This will make sense. Now am I out of time? Okay, I'm out of time. So this is actually a good place to stop because there's these examples I want to go through of using gates. So we'll go through some of these, and actually there's some handouts, and you guys don't have to print anything. I'll print all this stuff out. I'll print it out and bring it on Monday. But there's a couple exercises I want to go through. This, when you get a second, look through this, and it just kind of shows you how you build the Boolean expression from these gates. So I can represent this circuit just using this expression right here. So we want to practice doing that, and we'll do that on Monday. So sorry I went over a little bit. Does anybody have any questions or comments before we sign off? Okay, well, thank you guys for hanging in there with me. I don't know what the other classes are doing, but if you joined and you didn't have to, I really appreciate it. And I guess Monday we'll see if anybody, the little puzzle that one of your classmates put out, they want you to decode something. So we'll see if anybody decoded that. My nephew showed me an easy way to do it, so maybe I'll share that with you guys. Have a great rest of the day, great weekend, stay safe, and I will see you on Monday, face-to-face finally.